Right, so now welcome back to our class. So last week, before the semester break, we have looked at chapter 4, the input, output, and peripheral. And we used this microcontroller, which is an ARM-based architecture, yeah, the LPC 17668 microcontroller by the uh, NXP, formerly known as Philips, yeah, by Philips. So this is one of the many microcontroller out there, and it is ARM based. There are a lot of ARM based microcontroller out there in the market. So this is one of the microcontroller, which is a 32-bit microcontroller, which is quite big for the uh, uh, relatively big for the microcontroller. So last week you have been introduced uh, to the microcontroller, the LPC one. This is not 1678. Sorry for that. This should be 1768. Yeah, 1768 microcontroller, and this is with not which but which, yeah, the width of the pulse, so correction. So again, last week you have been introduced to the LPC 17688 microcontroller, and we have learned also the memory map IO, and today we will continue with uh, the ARM embed, the digital IO, analog IO, uh, the PWN, and the programming techniques. So before we go to the ARM embed, uh, let's have a little bit revision on this, because we have one big week break. So it's good to review what we have learned last before the break. So again, this is the architecture of the LPC one. Again, this is 1768. Okay, the most important thing is here is that the memory map IO, where the IO, yeah, the connection to the outside is actually uh, mapped to the memory. Okay, so it is mean that when we want to communicate with the outside or with other peripherals that are connected to the microcontroller, so we need to access the address of that particular peripheral or the IO uh, within the memory range of the microprocessor, microcontroller in this case. So for example, our ARM microcontroller, the 32-bit microcontroller, the ARM embed M3 in our case. So the address size, the size of the address is 32-bit. That means that we will start with address 0, and all here is 32-bit, and we have 8 hexa digit from 0 to this F F F F F F F F. This is the last address, and all of these are 4 GB. So here we did this. There are many uh, partition which is dedicated for certain specific application. So for example, here from 2009C000 until uh, the address just before this, because this one is the new one already, uh, is reserved for GPIO, right? And last week we have learned already how what we have in GPIO. And also, if we look at this area, this is the peripheral, we call it peripheral 0, this is peripheral 1, and within this range, we have many more peripheral that we can access. Yeah, for example, here in ADC, yeah, is between the address 0, 4003, 4000 until uh, the address just before this one. All right, -1, this one -1, that will be the ADC, and we have many more. So last week we have learned the GPIO, and we go very detailed on this, where the address of the port that we have. Uh, we have 5 port for GPIO, which is port 0 to port 4, and each port has 32-bit in size. Yeah, bit number 0 to bit 31 means that we have 32-bit, and here the blue color here is representing the bit that is or the bit that has physical connection to the pin, to the microcontroller pin, right? This gray one is not available or not connected to the pin, so meaning that you cannot use this, yeah. And here port 1 we have only this part, and certain pin here that are connected to the pin, and here this part only, here this part and this part. And also we have learned that each port is further divided into 4 bytes, where we have, for example, here port 2, bit number 0 to bit number 7 is called byte 0, 8 to 15 is called byte 1, 16 to 23 is called byte 2, and 24 to 31 is called byte 3, right? So this is uh, for us to easily access each port, better divided to 8-bit. So again, in memory, we draw like this. So and we know that in memory, each location is 8-bit size. So for example, if we take port 2 in memory, so this will be 4 byte for one port. So let's say this is mapped to what we call port 2. So this will be byte 0, this will be byte 1, this will be byte 2, and this will be byte 3 in the memory. And the address, for example, we start with let's say address, in our case byte 2, port 2, we need to look at the manual, yeah, to get the correct address. So where to get the manual? You can go to the internet and search for the LPC 1768 user manual, right? So for example, in this case, okay, you go to the internet and search for the LPC 17668 user manual, and this one should be, yeah, the user manual, and you can find the port. The name is FIR FIO, in our case by port 2 pin, port is pin, and by 0 click 0. So this is FIO2 PIN 0 is port 2 by 0. Yeah, so last week we have learned that here this, yeah, the port is represented by this register, the name FIO 0 PIN 0 means that this one is port 0 pin 0. So in our case we want to look at port 2, right, by 0. So we need to look at FIO2 means that port 2, PIN 0 is byte 0, and this is the address, the actual address of this port. So in this case, the address is, where is it? Here, 2009 C054, yeah, 2009 C054. So this is the address. Means that byte 0 here, the address is 2009 C054. C054. And the next address will be the byte 1. So which is 2009 C055. And if you look at the manual, 55 is FIO2 PIN 1, means that this is port 2 byte 1, and of course this is port 2 byte 1, and the next one is byte 2, and 56 is byte 2, and 57 is byte 3. Okay, so this is byte 2, and you will have byte 3, 57. Okay, so that is mean by this, yeah. So it is mapped to the memory, and each byte, yeah, is has a unique address. Means that when you access this address, this location, it will access this byte. Whether you want to read from here to the microprocessor core, or you want to write from get the data from the microprocessor to the memory. So how to read? So to read the data is easy. We have learned this already in chapter 3, where we use LDR instruction, right? LDR to read from memory to the microprocessor register, whether R0 or R1 or R2, so we call it Rn. Right? And if we want to save the data or send the data to this port 2 by 0, so we can use str store instruction. Okay, so that is means by this port. And we have learned also how to configure the port, right, or the pin to be an input or output pin, right? And remember, the pin is physically connected to the bit in the port. Yeah, for example, in this case, if we have this one is port 0, byte 0, and this is bit number 0 to bit number 7, 1 byte. Yeah, and this is the address in the memory. So this is the data direction register. Yeah, this is the direction register where it is used to control whether the port, sorry, this is the port, to become an input or output port. So for example, we want to set this one, this part, this 4-bit as an input, and another 4-bit here as an output. So what to do is we need to set or we need to clear this bit, the corresponding bit here in FIO DIR register. So if we put 0 here, means that bit number 7 here will be the input pin of bit. And here 0 also means that this one also input, this one also input, input, output, 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 and output. This is the pin orientation of the microcontroller, the LPC 1678 68 1768 microcontroller. So for example, here, yeah, the IP26 P2.0 here means this one is port 0, bit 0, right? And for here, P2.8 means that this is port 2, bit number 8. So bit number 8 is in byte 1 already, yeah? So in this representation, is it not represented in byte, yeah, byte 0, byte 1, byte 2? No, it is in 32-bit. That's why we can see that P1, port 1 here, we have bit number 0 until here bit 31, right? So means that if bit 31, this is in byte number 3 already, right? So if we want to access this, for example, if I ask you where is or what is the address of this pin, how to access this pin. So to do that, we need to identify where is P1, port 1, bit 31. So if we back to this, we have our register here, or a port here, which is 32-bit, where this is bit number 0 and this is bit number 31. And for example, this is port 1 in this case, because we are looking at P131, right? P1 bit 31 means that this bit, all right? So how to access this bit? So we need to know where is the, or what is the address of this. So first thing first is that we need to identify this one is belong to byte 3 of port 1. So the to determine the address, of course we need to go to the, or we need to use the manual, and the name of this byte of port 1, byte 3 of port 1 is FIO 1, meaning that is port 1, PIN 3 means that byte 3. All right, so look at this. So we are looking at FIO 1 pin 3, which is this one. Yeah, 37, yeah, C037. So this is a register for memory location in 8-bit. Yeah, this one we now we have 8-bit, and this is at address 900 2009 C037 2009. This is the address, and this is the bit that we are looking for, and this is actually bit number 7 of this. Yeah, so if we want to access this this means that we need to go to this address and look at bit number 7 of this memory location. So meaning that this is connected to this pin, this one, right? Same as this one. If this one is P1 30 means that we are looking at byte number, this byte also byte number 3, but bit number 6 in this case, because this bit number 6 is actually bit number 30 of port 1. Okay, so that is how we access the microcontroller pin, right, through the memory. Okay, now if we know that already, then we want to write the program to demonstrate or to use or to apply what we have learned just now. So for example, we want to flashing the LED that is connected to pin DIP21, right? It's just like very simple application where we have our microcontroller. So we have the microcontroller, and we have one LED. And this LED is connected to which pin? DIP21. So where is DIP21? This is DIP21, which is P2.5. Here means that port 2 bit number 5. So this is P2.5. So first thing first is we need to locate, or we need to know where is P2.5. And we need to, in order to do this, we need to set this pin to be an output. Output pin, because we want to connect this to the LED. So first we need to know where is our pin located in the memory. So we have two registers that need to be accessed. So the first one is the direction register, and this is port number 2. So of course this is FIO 2, and the data direction register is DIR, and it is in bit or byte, byte 0, right? Because it is in bit 5, right? So bit 5 is in byte 0, yeah, this bit. So means that we are in byte 0. So if byte 0, so this should be 0. Okay, and the port, the pin is FIO 2 also, PIN 0 also, and bit number 5 should be here. So we have 0, bit 0, bit 1, 2, 3, 4, 5, 6, 7. If we have like this, it should be this bit. And here also we have 5, 8, yeah, 8 bit. And this is the one that connected to the LED. So in order to make this as an output, so what we need to do is we need to have logic 1 in the FIO to the R0 bit number 5, so that this one will be configured to output. Now if this is configured to output, so if we send 1 to here, yeah, if we have 1, here, we will set this to high, and because this is connected to LED, so this will turn on this LED, right? If we set this to 0, means that we make this low, and we will turn this LED off. Okay, so it's that that is the idea. And to write a program, of course, we need to know where is this, yeah, in the memory space. So again, we need to refer to the manual. So we are looking at byte 2, port 2, byte 0. Yeah, here, which is C2009 C054. So the address is 2009 C054, and here is this is pin. So this should be this one, and for this one should be two. Sorry, yeah, 54 is pin. Pin should be this one, 54, and this one should be 2009 C0. Again, we need to go back here, and this is dir, yeah, 40 C040 in our case. Okay, so now we know already the address of this, and we can write the program to turn on and turn off this already. So to turn on this just make this bit 0 or 1. But before that, we need to set this to 1 first. So there are many ways. All right. So first is you can send any number to here, but this one must be 1. You can put all 0, 0, 0, 0, 0, 0, 0, right? Or any number means that here should be don't care actually, right? Can be any number. So to make the things easy, because all are don't care, so we can send on 1 to this address, and we have this 1. Yeah, so we can have something like in any register. For example, in our R0 or R1, R2, you can use any one. So for example, we use R in our case, so maybe we use R3, or let's look in our case, our program, so that this is the same. Use R2. So we use R2. So we have R2. Remember, R2 is 32-bit. All right, but we only use 8-bit because our destination is only 8-bit. So we can have FF 8-bit here, and we can use store instruction strb store byte R2 to the memory location that is pointed by, in our case, we have this, the art is in R0, so R0 pointed to this. So we are in R0 here. This one is R1. Yeah, this one is R0. This one is pointed by R1. So okay, if we use this instruction, store byte R2, where our R2 is this FF, and we send to R0, where our R0 is this. Yeah, R0 have this. So we send this to this, and this will automatically make this as the output. And to on the LED or to off the LED, for example, to off the LED, so we can use R2 as well. So we can have 0, 0 in R2, and send to art1 because the output here, the pin here is pointed by art1. So this one is art1. So if you do this, we will have 0 here, and this will off. And if we want to on, so we just change the value here, and we can on. So again, to on, you can put any number because here is don't care. We don't use this one. But because in programming, we need to put the value. So in our case, we can use 0. Sorry, to on. We can use all are 0. And this one is 1, or all are 1. Also can, no problem. But let's, for example, we use this value. So we want to send this value to this register. So this value in hexadecimal is we miss one bit, yeah, bit number 4, right? 3, 4. We need to add one more. Okay, this is bit number 0. 1, 2, 3, 4. Another one. We have bit numbers. Okay, so this is number 5, all 8-bit. This should be 8-bit. And we have 2, 6. Oh, this is wrong. Let's change this a little bit. Okay, we have bit number 0, 1, 2, 3, 4, 5, 6, 7. And this is the one that we are looking at, number 5. And of course, we have number 5. And all here are 1, 1, 1, 1, 1, 1, 1, 1. And now we want to on this. So this one we put 1 here, and all, let's say we have 0. So this is in hexadecimal, we have 2, 0, yeah, right? So this is 2. This one is 0. So to have that, we have 2, 0 here in R2, and we send to R1 here. And this will make this to 1 and will on the LED. So that is how it's work. So in the program, this is the program to do this. So first we define the address of our this FIO2 DIR0. The address is this FIO2 PIN0. This is the address, yeah, 40 and 54. Now the pointer, we use R0 to hold the address of the data direction register, and the port, yeah, the pin is in R1, and here we have FF to R2, and we send, yeah, store byte, we send to R0, yeah, and R0 is indirect addressing, means that we send to the memory address pointed by R0. So R0 have this, So this will exactly do this. And now we want to flash the LED. So means that we send this one is to turn on. Yeah, 20. Why 20 here? Because here we want to have 1 and all other bits are 0. So that's why we have 20. And we send to this address. So and the address is pointed by R1. Yeah, here. So we send to R1 and we have turned on the LED. And of course, because the microcontroller run very fast, so we need to have a little delay or little break here, right? And the delay uh, function is created by a subroutine here, right? Where you call this subroutine name delay. So to delay the microcontroller, so normally we create a counter, right? So that the microcontroller count the number here. It will take some time to finish, and it will give you some delay here. So in this case, we have this value in R3, and we sub by 1, and we check whether the content of R3 is equal to 0 or not. If not equal to 0, we go back, sub again until we have 0, and if 0, we go back to this, where we turn off now. We send R0, we send 0 to R2, right? Immediate value 0 to R2, and we send to the output here. And again, we delay a little bit, and we go back to the loop and on back, on here, delay, off, delay, go back on, right? So this is how we access the microcontroller pin, right? So this is the address, yeah. So you need to know how to use the manual, how to locate, where is the port, where is the address that that you need to use in order to write the program for this. Okay, so that are the things that we have learned last week actually. So any question on that? Uh, we also have looked at the simulation in Kill Mu Vision. So let's look at this again. Last week we have so this is exactly the same program, except that I changed a little bit on the delay routine. Instead of this, I changed to this value so that we have more delay time, right? So let's look at the simulation. Okay, now the simulation we can look at the GPIO by selecting this port 2, so you can get to this, where you can look at the content of the direction register here, 32-bit, and also the pin here, right? And the pin that are available for this microcontroller is for port 2 is from bit 0 to bit 13 only, right? Exactly based on what we have here, bit number 0 to bit 13. So when we run the program, we can also look at the memory, the actual memory location for this, where FIO DAR is at location 40, right? So where is that? Let's have a little bit. Yeah, here is the location of this, and for the pin is 54, which is this one. All right. So when we run the program, we can use this, yeah, run, or press F5, click this, so we can see that now the location 40, 2009 C040 is FF. All right, so this is FF because we have this. We do this. We set FF to what is pointed by R0, and R0 is this, right? That's why we have FF here. And look at this. Yeah, by 0, bit number 5 here is on and off. And you can see the number here is 00200020. Okay, so that is what is happening in your microcontroller. So this is the assembly language. Actually, we can, and of course, in this chapter, we will use C programming instead of assembly programming. Yeah, because assembly programming is quite difficult and take more time to code, and this is not very suitable for very complicated program, except that we want to have a very optimum, very fast, very optimum program at in certain application. All right, then we need to use the assembly language. So in many application, it is better to use high-level programming language because it is easier to program. All right. So in this case also we can use C programming. Yeah, in this case is C++. So this is the same program, same application uh, written in C programming. Okay. So we have one function here, which is the delay function, right? So when you look at this delay function, right, we will not go into detail how to write the C programming because you have learned this in computer programming, so you have the knowledge already. Yeah, this is this in this course we need to apply what we have learned in computer programming in programming the hardware, right? So we have the delay function here, and this is the delay function where we count a number, yeah, from this value FFFF, yeah, and we count from 0, yeah, start from 0 to FFF, or you can count from FFF to 0 where you need to deduct here. In this case, you plus, and this is the main loop. So for the main loop, you need to have this, yeah, while one in bracket 1 in the in this means that this one will be repeated endlessly. All right, it's just like in assembly language that you branch and loop back to top again, run and loop back to top again. So in C programming, we use this, while one, and we have this. So this is the main loop, and before that we need to configure the port to be the output. So it's actually the same concept that we use in the assembly, but in C we need to use this, and this one is actually uh, using uh, the built-in library, yes, we call CMSIS, yeah, using this syntax. So this is LPC GPIO 2, means that we want to access byte port 2. LPC GPIO 2, this means port 2, and this is byte 0 of the FIO DIR 0, right? So this is a little bit different from what we have in assembly language here, where here we name it directly because we have what do you call it? We are free to choose the name, right? And we access directly to the memory. But here we're not accessing the memory, but we need to know where is it. Yeah. So the name is this, means that we access port 2 byte 0, and the size or uh, the content must be FF according to this FF. So we set all the pin to at port 2 byte 0 as output. And in the main loop, what we do is, yes, we do the same. We set this to 20. Yeah, pin GPIO2 byte 2 pin 0, means that byte 0 20. This will turn on the LED, and we have the delay. We call the delay function. This is how we call the delay function. If we go to this and do this and go back, and if we have this, turn off, we have 00 sent to the port 2 byte 0, and we turn off the LED. So this one, if we do the simulation, we will have the same output as the assembly language 1, right? So this is the initial value of the output port, and this is the direction register. And if we look here, this is the disassembly window here. So actually we can look at the equivalent assembly language for this one. Yeah, please remember that when you write in C or any other high level language programming, so it is actually converted to the assembly language before the microcontroller can understand what you write in the high level language, right? Because this is the language that the microprocessor understand, the assembly language. And of course, this assembly language is translated into the machine language here, right? So this is the machine language. So this is the assembly language. This is a little bit different that if we compare this to what we do in here, right? Because this one we write our own program, and this one is translated by the software, yeah, the compiler, which translate or convert this C code into the assembly language. So it is depend on the compiler that you use. Yeah. So this means that if you have a very good compiler, so your program, the C program, will be converted to a very optimized, very good assembly program, right? But if you have knowledge in the assembly language, you can have your own version of program using assembly language, which is can be fully optimized. Yeah, means that you not depend on computer to optimize your code, right? So now let's run the program and see what happened. So we will have the same output here. This one is turned on and off, 20 0 20 0 20 0, and here we have FF, right? So from now on, we will use C program, yeah, to program our microcontroller instead of assembly language. Okay, so that is the things that we have learned last week actually. So we are now at 9:35, so we will have 5-minute breaks and come back. We continue with chapter with the next section.